So good afternoon, everyone. Thank you for coming. A great pleasure for me to introduce our speaker today, Professor Giacomo Di Marco, from the University of Ferrara in Italy. Professor Di Marco is department head of the Mathematics and Computer Science Department at the University of Ferrara, and also director of the Center for Modeling, Computing and Statistics. He's also associate editor for the Journal of Computational Physics. And he has done a number of contributions in the general area of applied and computational mathematics, and in particular, the numerical solution of partial differential equations and kinetic theory, Monte Carlo methods, plasma physics, and uncertainty quantification. So today he's going to tell us about some of his work at the intersection of numerical solution for partial differential equations and kinetic theory, which is, for those who work in the area, they probably know it as Boltzmann equation and kinetic models. And so we look forward to hearing from him.
So thanks a lot, Nicholas, for the nice introduction. So I'm very happy to be here at MIT, the first time for me to visit this nice, very nice place. So before starting, I would like to acknowledge some of my colleagues that collaborated with me to this research. There's Walter Boscheri from CNRS in France. Nicolas Cruzel is at National Institute for Research in Informatic and Automatic in France. Lorenzo Pareschi is in Edinburgh, UK, Giovanni Samei in Belgium, and Pierre de Gonde, who is at CNRS in Toulouse and also at Imperial College in London. So, before starting, since my university is pretty small and also the city where I work, I would like to show you, so where is Ferrara? Ferrara is over there, is located between Venice and Bologna. It's a small city, but the university is quite old. It's been founded in the 14th century, so it's 650 years old and founded by the Pope. And this in the bottom is a picture of, not of the university, but of the castle of, our city, just to clarify a little bit where I come from. So just the outline of what I would like to discuss with you today, apart from the introduction, which will be about Boltzmann and the equation and some related models, so about kinetic equation. What I would like to discuss with you are some recent development about how to face the challenge of simulating such a complicated equation, and what is the importance of doing that. So the two classes of methods that I will discuss, the two main classes are, the first one is a stochastic kind of method, like direct simulation Monte Carlo and related hybrid methods. And then I will go to some deterministic scheme, both still particle method, but from a deterministic point of view. And I will discuss at the end some high-order finite volume and DG schemes. So now let's go to the main point. So kinetic equation is what you see in the first equations that you see in this slide. So it describes the time evolution of an unknown, which is f, which is a probability density of the particle. So f describes the probability of having a particle in a given position of the space x with a given velocity v at a given time t, and so it's a probability density. But even if we give a look to the problem from a probabilistic point of view, the equation to which this unknown obeys is a deterministic one. And you see it here. So you have an hyperbolic term on the left-hand side, tells you that the distribution moves with a given velocity v, and on the right-hand side you have what is called typically a collision or interaction term. It's already written in a non-dimensional way, And what appears in this type of scaling is this number epsilon, which is a non-dimensional parameter known as the Knudsen number, which is proportional typically to the mean free path. So as you can see, the equation lives in a 7-dimensional space. So we have 3 dimensions for the physical space, 3 dimensions for the velocity space plus the time. So it's a very, from one side, well-known equation, and apart from being used to describe gases, rarefied gases or fluid dynamics problem, it's also very often used to describe other kind of physical phenomena, ranging from the classical physics to plasmas, but also it has been used in the past to describe problems ranging from biology, medicine, social sciences like opinion formation, wealth distribution, and etc. So it's a very, very powerful, in some sense, way of modeling many different problems. But here today we would like to discuss how we solve from the numerical, how we can solve from the numerical point of view such an equation. And I will focus on the problem of rarefied gas dynamics. So apart from this kind of scaling, which is, as I wrote, is a fluid dynamical scaling, you can write it also with a different kind of scaling, like typically a diffusion scaling. If we use this kind of, this different point of view, we can show that this equation in some, when this number takes some precise value, is equivalent or to, well, compressible Euler equation, or to the classical compressible Euler equation, to Navier-Stokes equation, or even to incompressible Navier-Stokes equation. So embedded in this model, there are many other classical fluid dynamical models. And one of the main goals is to be able to describe from a numerical point of view, so to derive numerical scheme which are able to be consistent even with this model that I will describe a little bit more in detail later. So the structure of the collision operator, so what you see on the right-hand side, depends on the choice of the particular model. In the classical rarefied gas dynamics, we have the classical Boltzmann collision operator, which is a 5-fold integral in the full 7-dimensional case, which tells you that typically tells you that you have 2 particles that meet, you have a collision, and after the collision you have what is called the post-collision velocity, which is V prime and V prime style. B is a kernel which characterizes the type of interaction that you can have, and the post-collisional velocity are written here down. So as you can see, so the structure of the equation is not so complicated in some sense. You have a linear hyperbolic term on the left, you have a relaxation, so term on the right, but the equation is, by the way, very computational demanding, because if to solve it you need well, to face the fact that you live in a 7-dimensional space, and you would like also to deal with the conservation, because everything here has to be conserved. You want to conserve mass, momentum, and energy. The velocity space is unbounded typically, and so you have to bound it in some way in order to solve it from a numerical point of view. You have different scaling, and typically you have different temporal and spatial scale. You typically have the fact that the collisional scale is different from the transport scale, and when you are close to the thermodynamical equilibrium, this parameter is close to 0, and so you meet what is called in the numerical mathematical community a stiff problem that you want to solve. Apart from that, okay, here there are some details. So the collision operator in general satisfies some local conservation properties, and so it conserves exactly mass, momentum, and energy. And also you can show that some entropy inequality hold true. This means that the kind of function f, which are such that the collision operator is 0, are always Maxwellian distribution, which are or Gaussian distribution if you prefer, which are function in the velocity space which depends only on density, momentum, and energy, where the mass, the density, the mean velocity, and the temperature can be obtained from the distribution function f by integrating it in the velocity space multiplied eventually by some function which depends on v. Again, if you integrate this kinetic equation against what are called the collision invariants, you end up with a set of macroscopic conservation laws, which are not closed, by the way. But you can observe then when you are close to the fluid regime, so when the collisional rate becomes sufficiently high and the mean free path between two collisions reduced to 0, you get that typically Q of f is equal to 0 and f is projected to a Maxwellian state. And in this case, you can, at least formally, but eventually or even in a rigorous form, you can show that your kinetic equation is completely equivalent to the standard compressible Euler equation. So embedded in the solution of your Boltzmann equation, there is also the solution of the compressible Euler equation. But you can move even further and show that when this Crucian number is not 0, but is close to it, by doing some type of expansion called Chapman-Enskog, you can also show that your kinetic equation is equivalent to a compressible Navier-Stokes equation. And one of the goals of solving from the numerical point of view this kind of model is that you want to build a numerical scheme that is consistent, of course, with the original equation, but is also consistent with the compressible Euler equation or the compressible Navier-Stokes equation, or eventually also with the incompressible limit. This is why, because typically if you face a rarefied gas dynamic problem, what you want, let's think to a re-entry problem, you pass through all these kind of regime. So you would like to use the same model and the same numerical method to solve all the different regimes that you typically meet in this kind of problem. Okay, so this was a pretty long introduction, but I want to stress a little bit the problem before going to describe some main ideas. So from now on, I will just give you some idea of how we can build numerical methods which are able to efficiently and eventually also with accuracy handle this kind of model. So the classical Monte Carlo or direct simulation Monte Carlo method is quite simple. You replace your distribution function f by a finite set of particles with a given position and a given velocity. And then the equation is equivalent, so the Boltzmann equation is equivalent to just push particle with a given speed. You can call it a transport step. Then you have to sort particle into the cell. And to solve the collisional part, you select and execute random collision between the particle which belongs to the same spatial cell. Then at the end, you compute eventually some average statistical value, like typically the density, the momentum, and the energy, which describes you the state of the system during the time evolution of your problem. Eventually, you have to handle also boundary condition, like if you have an object that I will not enter into the detail here. So these is the classical Monte Carlo methods, and why you use it? Because as I said, the computational complexity of this kind of problem is very, very high. You want typically to solve a 7-dimensional problem. So as is well known, Monte Carlo methods are quite fast compared to standard, let's say, deterministic method, even if the error of this kind of simulation scales with 1 over the square root of the number of samples that you use. Okay, so the error rate is quite high, and you observe typically a lot of fluctuation in the solution. And if you want to eliminate them, well, you have to increase this number, and then also again the let's say the computation becomes more expensive. So just to enter a little bit into the detail of how it works when you want to do a Monte Carlo simulation, well, you have just a push particle, but from the collisional point of view, what you have? You have a collision operator which typically you can divide in two parts. One is the gain, is called the gain part, and the other is the loss part, which has typically this structure. So Boltzmann equation can be written in this way, with P is what is called the gain operator, the gain part of the collision of the Boltzmann equation. And if you want to, to solve this equation with the particle method, you can think to use a given time integrator like forward Euler scheme, very simple, and then you have a probabilistic interpretation. So, which tells you that with a particle which has a given velocity vi will not collide with this probability, and instead will collide with the remaining probability mu delta t divided by epsilon, and the collisional law is described by the gain operator p. Which means that at Monte Carlo level, you have with some probability, the first one, you don't do anything. You sample from the original distribution. And with the remaining probability, you sample from the gain part of the collision operator. So you perform some collision, and then you sample from them. Of course, to have a probabilistic interpretation, this condition must hold true, which means that when you are very close to the fluid limit, the time steps goes to 0. So to perform a simulation with Monte Carlo, you have problem, because the equation becomes very stiff, and then you need an infinite number of time steps in order to solve them. So this was the classical Monte Carlo scheme. So what we can do to improve a little bit standard direct simulation Monte Carlo. One idea is to use what are called the hybrid method. So here we have a definition. We have a probability density F and the probability density M, which is the Maxwellian distribution, or equilibrium density if you want. You define a function omega, which depends on the ratio between F and the equilibrium, and you represent your solution as a combination of a function which I called f tilde, which I will be more precise later, plus equilibrium distribution multiplied by a function omega. If you want to enter a little bit more into the detail, if you define the function beta as the minimum of this omega with respect to the velocity space, and you can introduce a new probability density given by this f tilde divided by 1 over beta, and you have what is called an hybrid representation of your solution. So what I want to say with all these simple computation is that your distribution function typically can be expressed as a convex combination of equilibrium plus something which is not in equilibrium. Maybe here I have a picture which can show a little bit from a visual point of view what happens. So here you have a part of the solution which is in equilibrium, or maybe this Gaussian distribution, and the part which is not in equilibrium. And this happens every time that you perform a numerical simulation with Monte Carlo methods. So what we can do to improve standard Monte Carlo? Well, we can use this fact, and by considering this general representation, we solve the non-equilibrium part by Monte Carlo method, so by standard stochastical DSMC. And the equilibrium part in a deterministic fashion, like with finite difference, finite volume, discontinuous Galerkin, what you prefer. And so when you do that, you have a part of the solution represented by particle, by set of sample in your domain, a part in a deterministic way, so on a grid in your computational domain. That's what happens. Or maybe you can do something different. So instead of writing your distribution function f a convex combination of two distributions, you can write f as a sum of a Maxwellian plus a perturbation. The perturbation g now is not anymore a probability density. It can take also, and typically it does, take negative values. So you can show that by doing this decomposition, the distribution F and the distribution G, the perturbation, satisfies this coupled system of equations. So if we give a look to what we have here we have, for instance, the standard compressible Euler equation, and here we have a perturbative term. And we couple this with the standard, let's say, Boltzmann equation. So how does it work? It works in this way. You have your preferred, what you prefer to solve, what is your preferred solver for a fluid dynamical solver, like I don't know, Navier-Stokes. Even Navier-Stokes it works, or compressible Euler equation, finite volume. And to this solver, you add a new term, which is discretized exactly as the flux F. But the only point is that this new term takes information from the solution of your Boltzmann equation solved by direct simulation Monte Carlo methods. And so since G typically is small compared to M, it happens that this way of coupling the solution, it permits to improve the statistical error that you observe in standard Monte Carlo methods. So, well, here is the kind of discretization, so of decomposition that I showed you before. So you have your standard F, your Maxwellian, and the perturbation G. So what happens? What you see here is well, classical one-dimensional SOD test. So you have typically you have three waves which are forming, and on the left-hand side you have the standard Monte Carlo method, and on the right-hand side you have well, what I showed you before, this with the system coupled with macroscopic solver plus the solution of the Boltzmann equation for different, from the top to the bottom, for different value of the Knudsen number. And as you see, well, you get the solution, you get much better solution by just using this idea of adding, I'll go back one second, by adding this new term to your equation where G is computed by the SMC. But still, you still have a problem. You are still solving, even in the thermodynamical equilibrium, you are still solving your kinetic equation, so you still have some computational cost related to that. So if you want to avoid also, when the mean free path is small, the solution of the kinetic equation, you can think about write some, let's say, complexity diminishing methods, which works well in this way. You still write down your distribution function f with the order composition. So you have a Maxwellian distribution and you have a perturbation. So you can then you observe, of course, then the perturbation. So the Maxwellian and your original function share the same moment. So the moment of f are equivalent to the moment of m, and you write down a new, let's say, kinetic equation for the perturbation g. Here you have a time derivative of the Maxwellian, which is, from the numerical point of view, is quite annoying to treat it. So you can use some, you use some math, and you observe that you can replace this time derivative of m by using this orthogonal projection into the null space of the operator Q. And at the end of the day, without entering too much into the detail, what you get is that you get a new kinetic equation for G plus your standard, let's say, your macroscopic equation, either compressible Euler or Navier-Stokes, plus a perturbation G. But now, the advantage of doing that is that when G is small, the number of particles that you use to compute G diminish as the Knudsen number approach 0. So as soon as you are close to the fluid dynamical limit, typically you don't have any particle in your system. And well, here is there are some detail of how you, at the end, what you get. You get from apart from the pushing of the particles, the transport phase does not change. Here is just the detail of the collision operator, which tells you that with some probability you just sample from the particle, from the perturbations that you have after the transport, and with the remaining probability you sample from a new kind of equation, which anyway goes to zero as the fluid limit is reached. So what happens? Well, I'm going to the detail of to the simulation now, and then I go back. It happens that here the test is a shock which moves from the left to the right. The continuous line is what you get in the fluid dynamical limit, and then you have the red line is the method that I'm going to show you now. I'm showing you now. And as you see on the right-hand side, you have the same with the standard Monte Carlo. You clearly see that well, the fluctuations are reduced, so you get much better result in terms of resolution. And if you give a look to the actual number of particles that you use to compute this simulation on the left-hand side, here the continuous line is standard Monte Carlo, and here is the real number of particles that you use, this is in logarithmic scale, by using this kind of complexity diminishing methods. And the different lines are for different values of the mean free path, let's say, or of the Knudsen number. So as the epsilon goes to zero, so as you reach the fluid limit, the real number of particles that you use is strongly reduced. So you get both things. So you get the fact that you have a reduction of the variance and also a reduction of the computational cost at the same time. So now I go back a little bit to the case because what I show you here, it was just for a simplified model, let's say a BGK model, which replace the standard Boltzmann equation with the relaxation towards the equilibrium. But you can do something similar for the standard Boltzmann equation. So you can derive a derivation of Monte Carlo method even for the Boltzmann equation. And how you can do that, I'm not entering too much into the detail because I'm running a little bit out of time and I want to discuss also other things. But you can use exponential integrator, and by using exponential integrator, you can get also a new Monte Carlo method even for the Boltzmann equation. And then use the same idea as I showed you before in order to couple macroscopic equation with fluid, so macroscopic fluid equation with kinetic equation. Okay, so second part. The second part is more about deterministic schemes. So I would like to discuss with you some ideas of how we can solve the same problem but with a different class of method, which belongs now to, in some sense, to standard more standard schemes like finite volume or DG, but even particle schemes. So the first part is about deterministic particle scheme. How does how deterministic particle scheme work? We discretize our Boltzmann equation by using a discrete velocity method. So we just put a grid in the velocity space. Then we employ a time splitting between transport and collision. We solve the transport part exactly because it's just we just push particle, and now they are deterministic particle with weights, and then we solve the collision part on the grid. And the initial data for the collision part is given by the transport, and the initial data for the transport are given by the collision part. So we introduce our Cartesian grid in velocity space. We replace f by a vector of size n, which approximates the function f at location vk. And by doing that, we get that our original, let's say, kinetic or Boltzmann equation is replaced by a set of n equations, which are just linear transport equation with velocity vk, plus a collision which couples all these n equations. And then we solve this set of n equations by deterministic particle method. Before describing the detail of that, I want to stress the fact that when you introduce a grid in velocity space, it happens something that is quite annoying. The fact that you lose conservation. You lose conservation of mass, momentum, and energy. Why? Because you just take one value in a grid point, you are obliged to truncate your unbounded velocity space, so you lose all the conservation that you know that are true at the physical level. So how can you restore your original conservation? You can build up a constrained optimization formulation and look for a new value of your function f, which is close enough to your original discretization, subject to the constraint that the moment, so mass, momentum, and energy, are conserved. This is an interesting formulation because you can show that you can solve it exactly by introducing a Lagrange multiplier method, and so you get the exact solution is given here, which means that you start from your original f, which does not conserve any moment of the solution. You multiply by some matrix which is pre-computed at the beginning and it does not change in time, and then you get your new function f, which preserves all the moments that you want. So now we go back to the solution of our equation. We need to solve n linear transport equation, and we solve it in a continuous way in space. So we define for each of these n equations a piecewise constant function in the three-dimensional space, which takes the value that you have at the beginning in the cell center. And then you compute the exact solution of the transport for the next time step. Here is a picture of what you get. So at the beginning you are in this situation. You have a piecewise constant function for every velocity. Then you push your reconstructed function, and what you get here is on the right hand side is the solution after the transport. So left before transport, right after the transport. So each discrete velocity drives the transport equation with a different velocity vk. The shape of the function not changed during the transport, but what it changes is eventually the cell center value that you use to compute the collisional part. So as I said, the collisional part is solved on the grid points. So we need to solve some ordinary differential equation. This was this five-fold integral that you have to solve. And for instance, you introduce some numerical time discretization. The first one is just forward Euler, or you can use some exponential integrator if you want to get rid of the stiffness of the equation in epsilon. And so you get something. The last line here is a scheme which is uniformly stable with respect to epsilon, and this also projects the solution over the Maxwellian distribution and the limit. And then you compute your collision operator by fast spectral method. So use a coupling of weighted particle plus spectral method for the collision operator. Well, here there are some details, but I will not discuss them. I want maybe to discuss the result. Here again is just one-dimensional test case, just to see what happens. We compare this, let's say, deterministic particle method with Wino second order, first order scheme for different regimes. Here there are some zoom of the solution, and as you see, when the Knudsen number is quite large, the solution is very accurate, the accuracy is very high, but when you are close to the equilibrium, well, you lose some accuracy, and the method is between a first order and second order accurate method. So what you can do to improve this result, the idea is the same as I told you before. So you know that the equilibrium part, in some sense, can be solved by solving the fluid equation. So you can solve this part with a macroscopic scheme. You have your compressible Euler equation, your preferred, let's say, numerical scheme code to solve your fluid equation. And then you use it. You use it to compute part of the solution. And then you compute your distribution function f as a convex combination of your transported distribution with the particle scheme and the Maxwellian distribution that you get from your preferred macroscopic solver for the fluid equation. And and then by doing this convex combination, you improve the method, because here, when you are far from, let's say, from the equilibrium, the scheme is accurate as a Wino solver, but also in the limit, you can show that the scheme is keep its accuracy, because the solution is automatically replaced by the solutions that you get with a standard, let's say, solver, macroscopic solver. Okay. And what about scalability? But the scalability is very good. Is very close to an ideal scaling, because everything here, what I didn't say is that this deterministic method is built on a Cartesian grid. So since it's built on a regular Cartesian grid, you can show that it scales very well with the number of core, typically very close to the ideal scaling that you can get. And if you compare a little bit for a four-dimensional simulation, so it's 2D in space and 2D in velocity, we're using by just 8 cores laptop. On a laptop, you can show that you can run a simulation with a BGK operator, let's say a simplified relaxation operator, just in order of minutes. But also the solution of the Boltzmann equation in 4 dimensions, it can be handled with just in some hour. So it's very fast, and is also very precise. Well, the negative part is that it works only on a standard Cartesian grid. And you can also run some full 7-dimensional 3D plus time simulation of the Boltzmann equation, well, on a grid which is typically 100 cube in space and 32 cube in velocity space by using an MPI architecture. Then you have some time steps, and the running time for the Boltzmann equation is 1 day. So, well, so the point that I want to stress is that we are able, in some sense, with this deterministic particle method, to run a real 6-dimensional simulation of the Boltzmann equation. But we are able to do it just so if you have complex geometries, then the problem is not solved yet. We don't know how to do it in the same way up to this moment. So the last part, I think I have still, 10, maybe 8 minutes. So the last part is, in fact, what you can do when you have complex geometries. When you have complex geometry, you can do still something. The price to pay is that the computational cost grows a lot. So in this case, what we did is just a 2D problem. So we are just in 2 dimensions, both in space and in velocity space. But we handled, let's say, arbitrarily shaped meshes. And these are the kind of meshes that we had are this polygon here. Okay. So here, well, we have a cell average, which is just the integral of fk over the space. Then we build up some high-order polynomial representation by using a central Wino reconstruction. And well, we integrated in velocity in space our discrete velocity model on each of the control volume. And what you get is a finite volume formulation of your scheme, of your problem, where L is just the flux function. Then, for instance, you can try to build up, well, you have to discretize in time, and you use a first order, for example, in time explicit discretization. This works, of course, but apart from being of first order, you still have the problem of the stiffness, because when epsilon, when this mean free path is very small, well, in order to be stable, the time step has to be very, very small. So you can avoid at least stability problem and handling many different scale by using different kind of time discretization, which are called here implicit, explicit discretization, can be either Runge-Kutta or linear multi-step method, does not change much. And here is one example. Capital F at bar are the stage values. This A tilde and A are the some coefficient of the Runge-Kutta scheme for the explicit and the implicit part, and omega tilde and omega are the weights of your Runge-Kutta schemes, which are coupled. You have so you solve part of the solution in implicit fashion and part in the explicit with the explicit method. And well, what are the advantages of doing that? The thing that you can prove that if you use the correct implicit-explicit discretization, you are uniformly stable with respect to the mean-free path, and you are consistent also with the limit, with the compressible error equation, meaning that in the limit, automatically, without doing anything to your code, you get a scheme which is consistent with the compressible error equation and which is also high-order, both in space and time. There are still some problems related to the fact that Q is implicit. And since Q, the collision operator, is quite complicated in some sense, you have some integral to solve. It's something that you want to avoid typically to use implicit scheme for the collision operator. So if you want to avoid that, you can use, well, here there are again some details that I can maybe not discuss. But what you can do is to rely on some penalization. So a penalization means that you have your original Boltzmann operator, you don't want to invert it with the implicit scheme. So what you can do is to add and subtract a new collision operator, which is much simpler and which share the same structure of your original operator. Typically, it has the same kernel. So meaning that the solution of your Boltzmann equation are the same as the solution of your new operator in the limit in which the mean-free path is 0. So you add and subtract this term, and then you handle the difference between your original operator and this new penalized operator in an explicit way. And you just treat implicitly the new, let's say, collision operator, which is much simpler to invert. And even in this case, you can show that, you can theoretically show by hand that if you choose properly your numerical scheme, implicit, explicit, you are consistent with the limit equation, and you are also uniformly stable with respect to the mean-free path. Well, just a couple of words about DG. You can think to use also, apart from finite volume, also some discontinuous Galerkin approach. So by resorting to a linear combination of basis function, you write down your weak formulation, and you get a discontinuous Galerkin method for your kinetic equation approximated with a discrete velocity method. But again, you have the problem of the stiffness of the collision operator. So you may use this kind of idea of implicit, explicit discretization. Here we use the multi-step methods to handle the stiffness of equation. And in the case in which you use also linear multi-step methods, what is very interesting is that you can prove, again analytically, that you are not only consistent with the compressible error equation, but if the initial data are well prepared to the Navier-Stokes limit, you can also show that your scheme is consistent with the compressible Navier-Stokes equation. Meaning that you are solving, if you are in the correct regime, also Navier-Stokes equation, without any, again, time step limitation of your problem. Okay, here is just some time comparison between DG, Runge-Kutta, and let's say multi-step methods. And well, the only thing that I want to stress is that linear multisteps are a little bit less expensive, and since computational effort is very important when solving Boltzmann equation, well, it's probably better to use a linear multistep method instead of Runge-Kutta. The main reason is that the Runge-Kutta schemes need to compute some stage value which are between the time level Tn and Tn plus 1, while the linear multistep methods use the solutions that you have computed as the previous time step, so you don't need to compute new solution in order to get the high-order discretization. Okay, here is just a visual comparison about what you get if you use finite volume compared to what you get if you use DS Monte Carlo schemes. So it depends on what you want to do. So if you need really a very precise solution, of course with Monte Carlo you cannot get it. But if you want something which is reasonable in a reasonable amount of time, well, maybe Monte Carlo is the good solution. Or these hybrid Monte Carlo schemes are also very, very, I think, interesting. Okay, let's jump to the conclusion. So what I've presented are some, I presented two classes of methods, some hybrid Monte Carlo strategies in the hydrodynamic scaling. So what I show you in the hydrodynamic scaling can be done also in some different scaling. So as I said, you can get some Monte Carlo methods of hybrid type even in the diffusion, or let's say in Navier-Stokes scaling, even if something that we have not done yet. And compared to standard Monte Carlo, the statistical noise is smaller, and also it diminishes when the scaling parameter decreases. They are also uniformly stable with respect to the scaling parameter, which is also very important. Or I also show you very rapidly some deterministic method. The first part is about first order, let's say fast, but first order, low order schemes, which combines spectral methods with semi-Lagrangian schemes. Or maybe you want, but they work only on regular Cartesian grid. If you want something that works for arbitrary geometry, you can maybe rely on high-order finite volume or DG methods using this idea of implicit-explicit discretization. Okay, so I think that I can end here, and thank you for the attention.
The hybrid methods that you use, well, first of all, thank you very much. Great talk. For the hybrid methods that you use, do you use the same grids for the DSMC and for the continuous simulation?
At the moment, yes, but they are not really related in the sense that you can even use a different grid. Then you have to interpolate anyway. But it can be done. It can be done, and it's definitely maybe interesting to do that.
Right. And there's just another thing for Michael. I'm sure it's a very obvious answer, but you said whenever you do the approach where you segregate or break the F into two components,
Mm-hmm.
You said that the component that deviates from equilibrium requires very few particles when you approach the continuum limit, which makes sense. What does it mean, requires very few particles? That to accomplish a certain level of accuracy, you do not need many particles? Is that what it means?
Yes, exactly. No,
Way of detecting the particles needed?
The point is important, I think, and well, it depends on what you want to do. So the sense is that one. So when you are close to equilibrium, okay, this peak maybe disappear. Okay, so it means that if you use the same resolution, so if you use the same weights, let's say for the particle, meaning that to describe a smaller peak, you need less particles. Okay. Or if you want to improve the resolution, you can maybe use the same particle, the same number of particles, and increase in the resolution. Okay, you can do both. Anyway, and to answer to the second question, yes, everything is automatic here. Okay, so is led by the scheme. The numerical schemes tells you how many particles you need to eliminate from your domain automatically, because it's given by you have a convex combination between what you need to keep and what can be cancelled. Okay, at least for simple collision operator. For Boltzmann is a little bit, no, it's not a little bit, it's much more complex, and there's still maybe an open question.
Any other questions?
Yes.
Yes, just follow Jaime's question. So for very small epsilon, you can use less particle, but the time step also has to be very small, right? So
Yes.
yeah, so how you deal with that?
It depends, in fact. So to deal with that, for instance, here there's, well, let's see if I have written here. Okay, here maybe it's written. If you use, what we used here is some exponential time integrator. If you use exponential time integrator, just you multiply your function by this exponential function, on the right and on the left, of course. And then starting from this reformulation, you write down, for instance, a Runge-Kutta scheme, okay? But with this reformulated equation. If you do that, what you get is already at the first order, you get something like that. As you see, you have a combination now of function which does not depend anymore on, so it depends on epsilon, but the coefficients are always between 0 and 1. Okay, so using this exponential time integrator permits to avoid the stiffness of the equation. And you get immediately something that when epsilon is 0, you project on this term. Okay? So you don't have any problem related to the stiffness.
But that is still the second term that divided by epsilon mu.
Yeah, but yeah, written this way is not nice, but this function, okay, goes to 1 in the limiter. Okay. Okay. From a numerical point of view, of course, is a problem, so you have to, but theoretically is okay.
Hi, thank you. Gosh, I'm curious to know, in what cases would you have indeterministic method work? Because you mentioned that part of the conclusion is that you're presenting the deterministic method. Are there in cases where indeterministic method will work for this?
Okay. Well, so let's say that we explored in this year both solution. We tried to solve this Boltzmann equation by Monte Carlo or by deterministic. Of course, there are some advantages in one class and some other in the other classes. So typically Monte Carlo or hybrid, they are faster. Okay, so if you need something fast, it's probably the right direction. But you have noise. So if the speed is very low, typically maybe you prefer something deterministic. If the speed of the flow is high, so like a reentry problem, well, Monte Carlo or hybrid Monte Carlo are good enough. Also because, and then it depends also on which kind of solution you are looking for. Because if you are looking for a steady state solution, well, then you can use Monte Carlo because you average over time. And so you don't need really to use deterministic. But it really depends on the problem. So low speed, probably deterministic. High speed, well, it depends on what you have to do. If you want, you need to be very precise, still deterministic, but then you have a bottleneck. At a certain point, the cost is, it grows too much. That's the point. So it's a decision about your computational possibilities, let's say, and the precision accuracies that you want. That's
Last question? Yeah, so in the hydrodynamic limit, like
Si.
you said that the deviation from the Maxwellian is small, but is it also right to assume that it's smooth? So that you could do a truncated moment expansion or something like that?
You can do a truncated model expansion. Yes, I think you can do it. You can do it. Yeah, you can do it. But if you truncate that's let's say an artificial truncation. Okay, so is the person that write down the moment equation truncate decide when to truncate. While the method that I show you today, you don't need to do nothing by hand before. Okay, so the scheme works independently on the choice of your mean free path and the rest. Okay, so they automatically, in some sense, adapt to the situations that you meet. So if you know exactly what to do, what we are doing, well, maybe like a truncation is maybe better. But if you don't know what is going to happen, like a reentry problem, you have different regimes, so then maybe this kind of scheme is better. They are better because they adapt automatically to the situation. Okay, that's the main point.
Thank you very much.
Thank you.